Okay, so today we're going to go over one of each kind of projectile motion problems. It's just Blake here, so for all of you that are watching this, I'm not crazy. Blake came so I wouldn't look crazy. Okay, so our first one here, we've got a horizontally projected rock. So thrown horizontally off of a cliff. Okay, we're told that it's thrown at 18 meters per second and that it follows a projectile arc and hits the ground 40 meters from the base of the cliff. Okay, so our initial set of givens is that we have two pieces of horizontal data. We know the horizontal velocity, which is not going to change. Okay, it's 18 meters per second. And we know the horizontal distance, or horizontal displacement. Okay, so that's going to be 40 meters. All right, vertically speaking, it doesn't sound like they give us anything, but we have to remember what we're always given for vertical stuff. That is, since it was thrown horizontally, VI is 0, and the acceleration is 9.81 meters per second squared down. Okay, so they are wanting me to find the height of the cliff, which is the same as the vertical displacement. Right, so I'm looking for D in my vertical information. If I'm going to find that, I need one more piece of information, probably time. I'm not going to calculate anything else. Okay, so I'm going to come over here, look at my horizontal information, and I find that I have enough of it there to get time because horizontally the object travels at a constant velocity, so v equals d over t. So if I manipulate for t, t equals d over v, that'll be 40 meters divided by 18 meters per second. So we have 40 over 18. So this thing is falling for 2.22 seconds. Now I've got my time. That is the one piece of information that is shared by both the horizontal and vertical parts of the question. Now I can use that in order to determine what the vertical height of the cliff is, or the vertical displacement. And for that I'll be using this formula, because I have VI, I now have time, I have acceleration, I have time. Okay, so I can use that formula without even having to manipulate it. So I'm going to plug in here that this is 0, so I'm just going to eliminate it. I'm not even going to do it. Okay. Hey, how's it going, Gavin?
Very good, and you?
Good. Now there's two of them. Now there's two people here. Okay. So we got 1/2 times 9.81 times the time squared, so 2.22 squared. So 0.5 times 9.81 times our answer, for all the decimals, squared. All right, so that means the cliff is 24.2, actually we only have two significant digits, so 24 meters. Right, so that's very much like the projectile motion question you'll get on your unit exam on Wednesday. Okay, so on this one, we have a projectile fired at an angle this time. Okay, so we've got this situation. Okay, so we know that the projectile is going to follow that arc. This angle is 40 degrees, and it's fired at 35 meters per second. That's a human cannonball. Okay? So knowing that, we're trying to figure out where the safety net needs to go and the maximum height of the human cannonball. So basically, like how high is the tent of the surface it was fired at, right? Okay. So we're going to break this up into our vertical and horizontal components. Right? Vertically speaking, horizontally speaking. So we have to remember about this vector that we always get for a fired at an angle projectile is that this side here is the horizontal component, and it represents the horizontal velocity of the human cannonball, which does not change. Okay? So if I want to calculate what the horizontal component of that launched velocity is, I'll use trig. It's the adjacent side, so I'll go cos of 40 degrees times 35 meters per second. Cos of 40 times 35. All right, so I've got 26.81 meters per second. Okay, obviously, I'll keep all those decimals for my later calculations. Okay. Then the other thing I have to remember is that this side, the vertical component, represents my initial vertical velocity, how fast it was going vertically when it left the barrel of the cannon. Okay? So to calculate VI, that's the opposite side. So sine of 40 times 35. Okay, so it's initially moving at 22.498, we'll say. Meters per second up. Right. So now I have to remember the rest of this stuff. I have to get all basically context. Okay, if this thing goes all the way up and all the way back down, safety net's also on the floor of the circus, so it's the same height as the cannon was. Then what's VF in relation to VI? Right, it's opposite, right? Because what goes up must come back down. And if it's doing the same kind of motion up and down over the same distance, it's going to come down at exactly the same velocity it left at, or exactly the same speed, sorry, in the opposite direction. And it does that, of course, because of gravity. Okay, so those are two things that I need to solve the question, but they're things I get from the context of the question, not things I necessarily calculate. Okay, so if I use these three numbers, can I calculate the total flight time? Okay, so that's my next step, is to calculate the total flight time. So that'll be VF minus VI over A. We're just manipulating our acceleration formula from Science 10. So that'll be negative 22.498 minus 22.498 divided by negative 9.81. Okay, so I'm going to shortcut on my calculator here. I'm just going to multiply that number by 2 and then divide it by 9.81 because that's effectively what's going on. Okay. All right, so this thing is in the air. The human cannonball is flying through the air for 4.587 seconds. Okay, that can come over here because the total flight time is the same for both the vertical and the horizontal parts. So 4.587. Okay, so if I want to calculate where the safety net needs to go, I just need to know how far the cannonball is going to fly horizontally. So D equals V times T. That'll be my 4.587 times 26.811. That'll give me my horizontal distance traveled and the location of the safety net measured from the cannonball. Okay, so taking that and I'm multiplying by 26.811. All right, so it's going to be 100 and, actually I only have two significant figures here, so it's going to be 1.2 times 10 to the 2 meters away. So that's the first part of the question. Calculated how far away the safety net would have to be. Now, the other part of the question wants to know what's the maximum height of the flight. Right, so now, one of these things, actually more than one of them, but one of them for sure, changes. Okay? VI is still going to be the same, because that has to do with the cannon, right? A is still going to be the same, because that has to do with gravity. What's VF going to be at this point in the flight? 0. Right? Because when I throw something up in the air, it goes up, it slows down, it stops for an instant before it starts to fall back down. So at its maximum height, its vertical velocity is 0. So I'm going to change VF here to be 0 meters per second, because at that point it is. So now I know VI, I know A, and I know VF is 0, and I'm looking for D. So formula I would use for that would be this one. VF squared equals VI squared plus 2AD. I could do another step and find, I could divide the time by 2 and use a formula that would get me the same thing, as long as I remember to divide the time by 2. And, so I'm looking for D, so I'm going to subtract VI over. So I'm going to have VF squared minus VI squared divided by 2A equals D. So that'll be 0 squared minus 22.498 squared, right, divided by 2 times negative 9.81. Squared divided by 2 times 9.81, so 19.16. Okay, so the maximum height is going to be 26 meters. We only have 2 significant figures. Okay, now, as I was saying, I could solve this using a different formula if I use half the time. Right? Then I could use this formula. D equals VI times T plus 1/2 AT squared. I just have to remember to divide the time by 2, and I'll get the same answer. We'll just plug that in just to show that it's possible here. Right, so that's 4.58 seconds there was our so. Okay, so there's half my time. That's how long it takes to get to the maximum height. So now I'm going to plug that into my formula here. So I'm going to have 22.49756634. That's my initial velocity times my answer plus 0.5 times negative 9.81 times my answer squared. Okay, and again, that's half my time. All right, I'll get exactly the same. As long as I remember to divide the time by 2, it'll work. The reason I don't show that very often is because most people forget to divide the time by 2. Okay. All right, so that's an example of a fired at an angle projectile, just like what we'll be on reviewing the exam.